Hey there, and welcome to this programming course for assembly language, using assembly language together with NESmaker. Now, we are going to take a little journey here, where we are going to really learn how to program in 6502 assembly language. Now, just to be clear, this is not a course to program an NES game from scratch. And in fact, if that's what you're looking for, then there is a great course over at the website called Pikuma.com. Now, this course will cover the entire process, programming an an NES game completely from scratch. Now, as you can see, this is a paid course. But if this is something that you're interested in, then I recommend it. I have taken this course myself, and it's really good. But we are not going to be doing that. We are going to be using NESmaker as a base. Specifically, I'm going to be using NESmaker 459. Doesn't matter too much, but that's what I'll be using. So that means that since we're not going to be programming from scratch, it means that NESmaker has done a lot of the heavy lifting for us. So we don't need to program screen update routines. We don't need to program routines for reading the controller or whatever. So the NESmaker has taken care of that for us. But we still need to know how assembly language works. We really need to know how that stuff really works. So we need to talk a little bit about hardware. Now, the NES has this CPU, the Rico CPU, which is a derivative from the 6502 CPU from MOS technology. So the details here aren't super important, but let's just mention briefly that maximum speed for the CPU is 1.79 megahertz. So it's pretty fast for a CPU from the early 80s. And it also has an integrated sound generator. So the sound chip is inside the CPU. And we're not going to be talking about it, but the NES also has a graphic chip called the PPU. So this is what the NES looks like on the inside. And here we have the 6502 CPU plus APU. Now APU, that's the sound generator. And here we have the PPU, the picture processing unit. That's basically the graphics chip. And then we have 2 kilobytes of RAM. So that's not a lot of RAM on the NES. Instead, there's a ton of ROM, read-only memory. Basically, the whole cartridge, or at least the base cartridge, that's ROM. But there are cartridges that also contains RAM. But again, let's not go into detail here. So why am I showing you hardware? Why are we talking so much about hardware? Well, basically, when we're programming in assembly language, we're programming directly towards the hardware. So we're constantly feeding the CPU and RAM with numbers. When we're programming in assembly language, it's all about numbers. Everything is numbers. We're going to look at that shortly. So here we have a brief overview of the CPU. So what I'm trying to show you here is that inside the CPU, we have these little compartments here. Now, we're not going to go into detail on all of these, but we are going to look at these first 3. This one called the accumulator, this one called the X register, and this one called the Y register. Now, I have put some numbers in here in binary format. we're going to talk about number systems in just a little while. But the point here is that inside the CPU we have these little areas. For example, the accumulator here, it can contain 1 byte. The X register contains 1 byte and Y register 1 byte. So again, we're going to look at this more in detail, but that's what's going on inside the CPU. We have these numbers inside the CPU. So let's look at a simplified version of that. So here we have a simplified version of the 6502 CPU. So here's the accumulator. Here's the X register, here's the Y register. Now each of these, like I said, can contain 1 byte. Now a byte is just a number, and it can be a number between 0 and all the way up to 255. Any number between 0 and 255. A byte can never go past 255. So we can't have the number 256, for example. We can't do that. So here we can have a byte here, and a byte there. And in fact, there's always a byte in there. Even if there's nothing, there's always at least a 0 in there, in all of these. So here on the other side, we have RAM. Now, I've just taken a random selection of the RAM. So on the NES, we have 2 kilobytes of RAM. Now, every single memory cell in the RAM has an address. So here, what I've written here, and this $sign, that means that this is a hexadecimal number. We often just use hexadecimal numbers when we're talking about memory addresses. So here's memory address hexadecimal 2000, 2001, 2, 3, and so on. So each of these is just a memory cell. And each, just like the CPU we were talking about a second ago, each of these memory cells can contain 1 byte. In other words, a number between 0 and 255. So a lot of the stuff that we'll be doing is juggling numbers between the CPU and the RAM. So for example, again, I'm using binary numbers. Don't worry too much about the details right now. We're going to cover those closer just a little while. But here I'm writing some assembly code. I say LDA and this binary number. Now what's going on here is that actually when I'm writing this, I'm feeding that number into the accumulator part of the CPU. LDA, that stands for load the accumulator with this number. So I put that number in here. By the way, just so you don't get too confused, we have 3 different number systems: binary, hexadecimal, and normal decimal. Now in this case I'm just using binary. But anyway, I'm loading that number into the accumulator here. Then here back in my assembly code, I write STA and then a $2004. That's a memory address. So first loading this number into the accumulator, STA store whatever's in the accumulator in that memory address. That means we just put it in here at that specific memory address. So that's a very, very simplified version of how assembly language works. But like I said, basically we're juggling numbers around. So we are, like I said, we're going to be using NESmaker. So I'm going to assume that you know how to use NESmaker. This is not a course on how to use NESmaker. So if you have used NESmaker, which I hope you have, when you want to run the game that you made some drawings, backgrounds, enemies, whatever. When you want to test your game, you click this little button up here, which says export and test. So you click that button. what happens when you click that button? Well, what happens is that in the background, NESmaker is collecting all of the different assembly files, because there are several assembly code files, putting all those files together into one huge file. That file will end up with something like this. Now, this is just a small part of it, but let's say that this is a huge file, huge assembly file. That file is run through what we call an assembler. Now, an assembler, that's just a tiny piece of software that translates assembly code into binary code, basically zeros and ones, because any computer can only understand zeros and ones. A computer can't understand LDA or whatever. So when you push the export and test button, all of the code in your project is put together into one assembly code file, which is put through the assembler. Tiny piece of software that translates your code into zeros and ones. And what you'll end up with is the ROM file, the .NES file, which we can use in an emulator to test our game. So the assembler part here, that's essential when programming in assembly language. So if you don't have an assembler, then you can't. You can write assembly code as much as you want, but you can't translate it into zeros and ones, because that's what the assembler does. And that's what happens when we run export and test. Now, in addition to that, the code is collected into one huge file, run through the assembler, translated into zeros and ones, and in addition to that, what NESmaker does, it does that, but at the end of that process, when this binary code, this ROM file is created, it also launches the emulator, the Messen emulator, and it automatically opens this ROM file, which will run your game. So that's what happens when you push the export and test button here. All right. So before we continue, we need to talk about number systems. Now, this course now at the beginning might seem a little bit technical, and I don't know if it's boring or not, but this is the kind of things that we need to talk about. Because if you don't understand the basics of what's going on here, then you can basically just forget about programming cool stuff in NESmaker. Because all of what we're going to be doing here has to do with numbers in one way or another. So I briefly mentioned it a minute ago, that when we're dealing with assembly language, we have three different number systems. We have the decimal number system. Now that's the number system that we use every day. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. Hexadecimal, that's a little different. That's a number system that has 16 digits, meaning we go from 0, 1, 2, 3, 4, 5, 6, 8, 9. But when we get to 9, we continue with A, B, C, D, and F. We're going to come back to that as well. And binary, that's just zeros and ones. And all the time we're talking about numbers like this, we're talking about bytes. So what I think we should do now is take an even closer look at the number systems. But before we look at number systems, let me just explain briefly how a byte works. So as said, it's a number between 0 and 255. So think about it like a wheel, like this. We start at 0, then we go to 1, 2, 3, 4, 5, 6, 7, and so on. And then we go all the way around here until we get to 255, 253, 254, 255. If we add one more number when we're at 255, then we wrap around to 0 again. And we continue with 1, 2, 3, 4, 5. So the same is true the opposite way. So if we count down 4, 3, 2, 1, 0. So if we subtract one more, then we wrap around to 255, 254, 253, and so on. So that's how numbers work in assembly language when we're talking about bytes. So it's 0 to 255. And like I said, if we add more, we wrap around this way. If we go the other way, subtracting from 0, then we just wrap around to 255 and so on. So just to give you a visual, just to show you how that works. So, right. Now we have these number systems. Like I said, we have 3 different number systems: decimal, hexadecimal, and binary. Like I said, decimal, that's just the normal numbers that we use every day. 0, 1, 2, 3, 4, 5, and so on. From 0 to 255. And by the way, I wrote 0 to 9 here, but we could have a number like 37, for example, or 163, and so on. You get the idea, right? But for hexadecimal systems, like I said, it's the same thing from 0 to 9. But the hexadecimal system, that's not 0 to 9, that's 0 to F. So when we go all the way up to 9 here, we continue with A, B, C, D, E, and F. So now going to come back to why we have these different systems in just a minute. But I said the decimal system goes from 0 to 255. Now the hexadecimal system does the same thing, but it looks different. So we go from 0 to 00 to FF. So FF, that's actually the same as 255. But in hexadecimal, 255 would look like this. So if this is the first time you're seeing something like this, it's probably a little confusing, a little weird, but don't worry. Once you start working with this, you get the idea pretty quickly. And another thing, when we're using hexadecimal numbers, we write a $sign in front of it, like I mentioned before. So when you see a number with a hex with a $sign in front of it, that's a hexadecimal number. And let me just do the last one as well. So binary. Binary, like I said, that's zeros and ones. Now when we're using binary numbers, we use a % sign in front of it. So if you see a number with a lot of zeros and ones and the % sign in front of it, that's a binary number. And when we're talking about binary, we go from 0, 0, 0, 0, 0, 0 all the way up to 1, 1, 1, 1, 1, 1, 1. And 1, 1, 1, 1, 1, 1, 1, 1, that's also 255. So these number systems do the same thing, but they just look different. So before we continue, why do we have all these different number systems? Oh, can't we just have one system? Well, here's the thing. You can use whatever number system you want. You can mix and match and whatever. Now, just doing that randomly like that, it's probably not a great idea, because your code might look a little messy, might cause some misunderstandings and so on. So I know a lot of people who only use the hexadecimal system when they're programming in assembly language. Whatever they're doing, they're only using the hexadecimal system. And you know, if that's something that you're comfortable with, then it's no problem. In the end, it doesn't really matter for the CPU. The computer or the hardware doesn't care, because when we're running all of this through the assembler, they're going to end up with the same number no matter what. So if we write 255, or we write FF or 111111, they're all going to end up with a value of 255. So, like I said, we can mix and match like that. But I find that they each have their own strengths. So, for example, let's take this decimal number system first. If I want to move a sprite around the screen, for example, I want let's say I want to place a sprite towards the top left corner of the screen. Then I want to use the normal decimal number system. So if I count in pixels, let's say 8 pixels down and 8 pixels to the right, then I want to use, or let's say 10 pixels down and 10 pixels to the right. Then I want to use the actual number 10 for down, the actual number 10 for right. That's so much easier to remember. Now if I was to do that in hexadecimal, if I wrote 10 down and 10 right in hexadecimal, and it would look something like that. So there we go. So if I wrote that, a dollar sign and 10, that's not 10. That's not the 10 that we know. 10 in hexadecimal, that's actually 16. That's a number that we know as 16. So the way the hexadecimal number works is that, let's if we take this number, well, let's just write a number like this, and we say, let's enlarge it, and let's just set it up like that. So the reason you usually see hexadecimal numbers written with 2 digits like that is because they're very easy to separate, this and this. So let's just count up here. We have 0, then we have 1, 2, 3, 4, 5, 6, 7, 8, 9. We're in hexadecimal now. So if I continue, it's A, B, C, D, E, and F. Now F is 15 because we always start counting from 0. 0, 1, 2, 3, 4, 5, 6, 8, 9. And then we have A, B, C, D, E, F. So F is 15. If I add one more to this number, then I get 1, 0. So that's why hexadecimal 10 is the number we know as 16. So the point I'm trying to make here is that using hexadecimal, for me personally, when I'm doing simple numbers like placing a sprite on the screen or whatever, then I like to just use my brain for other things. I don't like to convert numbers in my head when I'm doing complicated stuff like that. So in that case, I just use the normal decimal system. And if there's no reason for me to use anything else, then I'll just use the normal decimal system. If I'm just adding or subtracting numbers or whatever, then I can use the decimal system. So usually for me, I only use the hexadecimal system when I'm dealing with memory addresses or stuff like that. Now there are exceptions, we're not going to go into that right now. But the point is that the number systems each have their own strengths. So what about the binary system? Well, the binary system, that's a little more complicated. In fact, you probably have to look at it a little bit closer right now. So, one byte, excuse me, one byte, it's 8 bits. Now a bit is just a 0 or a 1. So here's 1 byte, 0, 0, 0, 0, 0. Now this could have been written as 0 like that in the normal decimal system, or something like that in hexadecimal. Like I said, it doesn't matter what system you use, but now we're talking about binary. In fact, let me just put the percent sign in front of it like that, which we do when we're dealing with binary numbers. Okay, so the point here is that this is the number 0 in binary. Now, when we're dealing with binary, we start from the right. So a bit is a 0 or a 1. This is bit number 0, as you can see up here. Then we move to the left, and this is bit 1. This is bit 2. Then we have bit 3, bit 4, bit 5, bit 6, and bit 7. Remember, we always start counting from 0. So this is how binary systems work. But each of these digits represents a value. So the one here all the way on the right, that bit represents the number 1. The next bit, bit 1, that bit represents number 2. The next bit, so bit 2, that digit represents the number or the value 4. Bit 3, this bit represents a value of 8, and so on. So how does that work? Well, this is a binary number. Right now it's 0. All of these digits are 0. If I wanted to write the number 1 in binary, I would have to write something. I would have to write this. This is number 1 in binary. Okay, that's not too hard to understand, right? But what if I wanted to write number 2 in binary? Well, that is the number 2 in binary, because this bit represents the value of 2. Alright, so what if we wanted to write number 3 in binary? Well, then I have to write a 1 here as well, because we're adding all of these together. So now we have a 1 here in the 1's place, we have a 1 in the 2's place, and like I said, we're adding these numbers together. So if I put a 1 in here as well, this 0, 0, 0, 0, 0, 1, 1, 1, that's 4 plus 2 plus 1. So 4 plus 2, that's 6. 6 plus 1 is 7. So this would be the number 7 in binary. If I put a 1 in here, then we would have 7 plus this 8. So that would be the number 15 in binary. And we can mix and match like that, and we can create all the numbers from 0 to 255 by mixing and matching ones and zeros like that. Of course, unless you're super interested in zeros and ones, you probably wouldn't want to do that, when you're just, like I said, placing a sprite anywhere on the screen or just adding numbers together. Doesn't make a whole lot of sense to use binary when you're doing that. And by the way, if I put a 1 in all of these, so we have 1, 1, 1, 1, 1, 1, 1, what number will that represent? That's right, 255. So, why would we use binary? Well, binary has a lot of uses. So, since each of these bits is only a 0 or a 1, we can think of those digits as switches, where when it's 0, then the switch is off. When it's 1, then the switch is on. So we could use 1 byte, just 1 byte, to keep track of something like, let's say you have a power-up system, where you want to have 8 power-ups in your game. So each of these bits could represent a power-up. Now, of course, we just have a 0 or a 1, so it wouldn't tell you a whole lot about what kind of power-up and so on. But I could say that in my game, this bit would represent the double jump shoes. This bit would represent the armor. This bit would represent a jetpack, and so on. And all I need to know is that, let's say the double jump shoes. Do I have the double jump shoes or not? Yes or no? On or off? So that's one way we could use binary. Right now, like I said, if this is completely new to you, then if you find this confusing, sure, I get it. This is, it's a lot when you start learning this in the beginning. So right now, the main point I'm trying to get across here is just to introduce you to all of these things. And right now, probably the most important thing to remember is that we have these 3 different number systems: decimal, hexadecimal, and binary. And if we wanted to, we can mix and match, but like I said, for me personally, I use the different systems when they make sense to me. So, those are the number systems. So, we've talked about a lot of things today, and I don't want to overwhelm you or make you sad in this first video. So, let me just say that learning assembly language requires patience and determination. You're not going to learn assembly language in a day or two. But we're going to do this together, and if you just put in some time and effort to this, I promise you're going to learn assembly language. So, let's round off today with a little game here. So, I made a short little game with this guy, Codeman, and he's going to remind us how the CPU and the RAM, how that stuff works when we're dealing with assembly language. So let's just get started with our little code man here. So here he is. Here's our little code man. So what we've got going on here is that we have some assembly language here on the top. Then we have the CPU here on the left, and we have a part of memory or RAM here on the right. And as you can see, we're starting from on memory address 0000, and we just go up one memory address at a time. And these numbers are in hexadecimal, even though I don't have this $sign in front of them right now. So what I'm going to do right now, or what CodeMan is going to do, is going to perform the instruction that I've written here in assembly language, and we're going to see how that actually works between the CPU and the RAM. So, and by the way, the A is the thing we call the accumulator. The X, that's the X register. The Y, that's the Y register in the CPU. Alright, so here on the top it says LDA hashtag $1F. Now let me just mention this while we're at it. When we write the hashtag like this in front of a number, that hashtag means whatever comes after this hashtag, that's an actual number. Now the alternative could be just removing that hashtag, and that would mean load something from the following memory address. So if you don't specify a hashtag in front of it like this, then the computer thinks that you want to load something from a memory address. But since I'm using a hashtag right now, that means the actual hexadecimal number 1F. Right, so LDA, load the accumulator with the number 1F. Okay, CodeMan, show us how it's done. So now CodeMan is going to fetch, CodeMan is going to fetch the number 1F. Sorry, let me just start this all over again. He's going to fetch the number 1F. There, he fetched the number 1F. And LDA means load the accumulator with that number. So now he put 1F into the accumulator. That's what this command does. LDA hashtag hexadecimal 1F means put 1F into the accumulator. That's it. That's what that command does. Alright, so let's move on. So the next command here says STA, store whatever's in the accumulator in the following memory address. Notice we don't have any hashtag right now because that wouldn't make any sense. We are going to store a value at a specific memory address, and in this case that memory address is 0013. Hexadecimal, of course, since I have this $sign. So CodeMan fetches whatever value is in the accumulator, and he needs to store that at the correct memory address, which is here, memory address 13. So he just puts the number in there. Basically, that means when we write STA like this, it means we're basically storing a copy of whatever's in the accumulator at that specific memory address, which was 13 in this case. So storing STA means storing that in that memory address. Alright, so what about this one? LDX 1B. LDX is basically the same as LDA, only that this time we want to load the X register. And notice another thing here. I don't have this hashtag in front of it. which means I'm not loading this number. I'm not loading 1B into X because I don't have a hashtag in front of here. That means load whatever's in memory address 1B. Load that into X. Right. So 1B. Let's go to 1B. That's over here. So he fetches that number and puts that in X. Again, we're just copying whatever's in here and put that in X. Load X with 1B. So just take what's in 1B, put that in X. Alright, so let's continue on. Now here it says STX memory address 24. Alright, so like before, we go to X, fetch that value, and store that in memory address 24. That's up here. So, storing X at that memory address 24, which actually means make a copy of whatever's in X at that specific memory address. That's what happens when we write it like this. So LDA, LDX, STA, STX, and by the way, we can use LDY as well. We're going to look at these commands closer next time. But like you can see, they're pretty simple, and right now they seem very similar. LDA, LDX, LDY. But there is a difference, and we're going to talk about that next time as well. So let's continue on. Now this is a special one. Now it doesn't say any number, it just says TXA. That means transfer whatever's in the X register into the accumulator. Transfer X to the accumulator, which basically means take whatever's in X and put it in A. And again, a number doesn't disappear from where we're fetching it from. We're just making a copy. But the command is called transfer X to A. So whatever was in X, copy that or put that into the accumulator. So this was just to show you, to give you something visual, to remind you what we were talking about in the beginning. So anyway, I think that's enough for today. So this is going to be a mini-series, going to be a few episodes. We're going to talk about this, and I feel confident that if you invest some time into this and you have enough patience, then you're definitely going to learn assembly language. So I think that's enough for today. So have a great day, and I'll see you in the next episode. Bye bye.